Yeah, it will just use the mouse and hit the right arrow.
I see.
Okay.
This is PDF, right?
No, this is PowerPoint. So for our animation, when you click, and you notice an animation, you might wait a second and see if it comes through. Okay.
This is part of the original PowerPoint. Oh,
it's the last one that navigated.
Oh, okay. Should I start?
Yeah, you can start whenever you're ready.
Okay. This talk is about proposing including this multimedia Steganalysis into the software IV&V process. And it's done by Dr. Qingzhong of St. Houston State University, previously a PhD student in my school, which is New Mexico Tech, New Mexico Institute of Mining and Technology. And Dan also with
now we can see it.
With the collaboration of Mr. Noble Nkwocha of NASA here. I'll go over the research we have done on Steganalysis in the last few years and see whether it makes sense to include this part as the software IV&V process. The reason is, increasingly the multimedia is used, encountered or interfaced somewhere, somehow in the software development process. And, the clean room methodology for developing software has other strict requirements on all sorts of things. And I personally believe this steganography will be an issue. It is really a problem encountered in cybersecurity, information security. But anybody who has to use software in their work should be concerned with the possibility that something more than meets the eye, whether it's image, video, or audio, or even ordinary document. Any file, any digital medium, in other words. Right, so we'll talk about what is steganography for people who have not paid attention to this this way of secret communication. Most of the time I will be talking about the methods for detecting steganography, which is called Steganalysis. Go over quickly the results on image and audio Steganalysis and discuss how this should be included. All right, I think everybody has heard about this one. We started thousands of years ago. Hidden writing or cover writing to achieve covert communication. In the internet age, the secret contents can be carried by any media that is digital in nature. Most common ones being the image, the audio, the video, but it can in fact be embedded in network packets, can be embedded in executables, can be embedded in ordinary text, can be encoded in somebody's DNA sequence. And there's endless possibilities of hiding your content to communicate on the internet. And with the recent disclosure of the government surveillance of the citizens' communications, there's some concern, in fact, pretty serious concern that this will go into personal devices, smartphones, and so forth. People want to use this to kind of encrypt their communication to avoid surveillance. And the thing is quite different from encryption in a way. You cannot see, you cannot hear it. There's an added level of security to the obscurity of it. even though it normally requires a secret key between the two parties to be able to encrypt and decrypt this content, which is a level of insecurity in itself. Anyway, the point is not to talk about the security issues here, it's to talk about how this may affect software. All right, so this is, go back. This is just one small example of embedding this whole text into this picture. Right, so this one is the original picture. And the second one is the picture with the contents embedded in it. So of course we cannot see any difference whatsoever, right? Making the detection issue really challenging. Here's another example is where this whole map is embedded into this picture. And the original picture may be called the cover. And the embedded thing may be called the steganogram. So the general problem is given a piece of multimedia, how do you decide if there is hidden content in it? So the problem, of course, is arbitrarily difficult in a way. There's no way. There's simply no algorithm for doing that. The payload, the embedded content, can be as little as 1 bit. Or other encoding algorithms will just do not alter the content at all, but use some other schemes to encode the content, right? Maybe somebody moving an object to the left means 0, moving it to the right means 1. In a sequence of these movements in a video, we encode content, right? So, so the problem is certainly very, very difficult. This picture simply shows, you know, the cover usually has no humanly perceptible difference with the with the steganogram, which of course is a basic requirement of steganography. And this thing really got a lot of attention since the terror attacks in New York. Well, today is the anniversary, I think, so it's kind of appropriate to look at what happened. After that, the media got really excited about this technology, calling it the poor man's cryptography. But in fact, what it was actually used, or how much it is used, nobody can tell you for sure. We just know it is being used. And this is taken on some terrorist training manual containing a section called how to do the covert communications and hiding secrets inside images. Images being the most popular because it's relatively small compared to videos, for example. This is another thing that hiding the picture, hiding one of these pictures in the other one. All right, so now we know the problem. The question is how do you detect? How do you detect the multimedia is innocuous or it contains unsavory, dangerous, or other content, right? In this day, the big problem is people will hide malware in images, right? And use some kind of phishing scheme to trigger you to input to take some user action to kick in the executable that is hidden as steganography. So basically, the research needs to address how do you detect image-based steganography and audio-based steganography and maybe other type of media that are used as covers. We've done a lot of work on the image and audio steg analysis. And with regard to detecting steganography images. There are two basic techniques. One is space hiding. That means simply modify the, for example, the least significant bit of each pixel. If you modify the least significant bit, the result will be invisible. And then you just retrieve the least significant bit of the pixels and then decode it or decrypt it, which is pretty simple to do. And it's also simpler to detect. In the worst case, you can just retrieve the least significant bit of the whole image, right? And then enumerate all the possibilities. Maybe starting from the first bit is the payload. You try to decode it. Maybe starting from the second bit, you have the payload and so forth. In reality, it may not be that simple, right? Because it's quite easy to encrypt your content before you embed it, right? So there's two levels. So the problem is much harder than decoding an encrypted message, because it's an encrypted message and then embed it into some multimedia. Right? The other technique is transform-based, right? For images like JPEG, which is compressed. The bits do not represent a pixel directly, right? Rather, we use the transform coefficient, ECT coefficient of A by A blocks in the image, for example. So to embed some content in those kind of format images, you have to do something else. And there are other ways, right? Maybe based on contents without altering the values of the bits altogether. But basically, we're going to look at the space hiding and transform hiding methods. So this is an example of least significant bit embedding, LSB embedding. It shows the different tens of the AB grayscale picture. By the way, in the research, a lot of the experiments were done on grayscale images. For the reason it's much harder to detect steganography in grayscale images. It does not have the correlation of the three different color channels in the color image. So in fact, it's a better benchmark to evaluate the effectiveness of detection algorithm. All right, so the schematic diagram how to modify this least significant bit to obtain steganography. All right, and there are a variety of methods to go about detecting the payload, detecting the presence of the payload. Usually it goes into a statistical analysis to extract the features and then you train a learning machine with sufficient data and then test the performance of it. There are a number of statistical methods, machine learning based methods for chi-square statistical analysis, which is rather simple. Just look at a chi-square statistic of the image you are analyzing to see whether it makes sense. Since if it's innocuous, then the distribution normally follows a certain pattern. Or about 10 years ago, there's the histogram characteristic function center of mass based technique. Again, this becomes a sort of a heuristic based on which to do the detection. And also higher order moment statistical model. It has to do with the moment statistical values of the probability distribution of, say, a set of innocuous images. You see whether the image under test conforms to that ordinary distribution. In LSB matching, which is least significant bit matching, does not alter the statistics, and the detection is much difficult. And we have a paper several years ago talking about LSB matching Steganalysis. All right, I think I should skip most of the technical details, just to specialize and not quite relevant to the larger proposal of including this activity as part of the IV&V. The point to take away is analyzing this steganography, analyzing multimedia for hidden content is very, very difficult. And so far, the research is still ongoing in all directions. One thing that we propose to take as a measure of evaluation criteria is the image complexity of the detection algorithm. A lot of the papers talk about the size of the image you are analyzing and also the hiding ratio. If the hiding ratio is very high, hiding ratio may refer to the number of bits that have been modified relative to the total number of bits, for example, or the number of PCT coefficients that have been modified in a compressed JPEG image, for example, and that's called the hiding ratio. Naturally, the higher the ratio, the easier it is to detect. And the image complexity, in fact, is an issue that needs to be taken into consideration when evaluating the effectiveness of detection algorithm, because image complexity is such that, for example, here, the image on the left is a lot simpler than the one on the right. That is formally described. You can see the shape parameter of the distribution of the coefficients in this image is much wider, right? So this is GGD, generalized Gaussian distribution in the transform domain, which can be used to describe the complexity of an image. For example, you look at the distribution of all these coefficients. And this power to the exponent beta, called the shape parameter, can be taken as a good measure of the image complexity. This scale parameter tells you how high the distribution goes. And so, for example, in this distribution, the beta value is smaller than the beta value here, which is still smaller than this one. Corresponding to these four pictures above, you see the one on the right has much higher complexity. The one on the left has the lowest complexity, according to the beta value, or the shape parameter of the distribution in the GGD. And in this paper, we have proposed using this image complexity as a measure to evaluate the effectiveness of detection algorithm. And the higher the complexity of the image, the harder it is to detect anything. Okay, so this again is rather intuitively correct. It's like you hide something, you hide a box in this building, right? And this building has 100 rooms of different size, shape, and color. Then of course it's harder for you to find the box relative to another building which has only 5 big rooms of pretty much the same architecture, then it's a lot easier for you to find something that is hidden there. That refers to the complexity of the image, the complexity of the structure. The hiding ratio refers to the size of the box. If you hire a big box in a pretty small building, of course, it's going to be a lot easier to find than you hire a tiny little box in a very complex building with a lot of room. Right? So the two parameters, the hiding ratio in our paper here, the image complexity, both need to be taken into consideration when comparing the performance of detection algorithms. And the reason it is important to identify all the relevant parameters is, in the literature you see a lot of papers, a lot of results, especially in this area of machine learning and pattern recognition. How do you compare the results? Everybody can claim their results is the best, and their conclusion is always valid with respect to the data they used, with respect to the algorithm they used. But how do you make an apples-to-apples comparison and make a fair comparison? Becomes an issue, not only in this steg analysis, also a general problem in comparing the performance of learning machines. Right? Do we have a fair basis for comparison or not? Otherwise, the conclusion doesn't really mean very much. You can always pick a machine to run on your own, maybe made up data to show your performance is better than somebody else's, which was done earlier. But we need to fix the common parameters to make a fair comparison. Anyway, to conclude this section, one basic heuristic is to look at the correlation of adjacent pixels in ordinary images, in innocuous images. Adjacent pixels are highly correlated, right? Indicated by this pretty bright band on the main diagonal, which represents a correlation of adjacent pixels. So if that correlation is much less apparent, then you can go ahead detect the hidden content with higher level of confidence. The image has been adulterated, right? Because the normal correlation between adjacent pixels has been violated. And, and there are a whole host of other issues, like feature selection. What would be a feature that we can use to detect hidden content, the steganography? But again, that's really a machine learning issue. Right? Since the interesting problem here is the raw data will just be the values of the bits and bytes, or the values of the DCT coefficients. It really doesn't tell you anything, right? And if you want to use all of them as your raw features, then they're really too big. So an interesting problem arises here is what is the methodology to, how do we extract features? What are the features? And the answer is features invariably involve the statistics, develop the features. It really needs prior knowledge. It's not really the ordinary machine learning. You can just throw in a bunch of data and the knowledge will come out automatically. No. Here is an example of prior knowledge. Expert knowledge is very, very important in developing effective machine learning algorithms, eventually formulate a detection algorithm for steganography. This is just a set of graphs showing the performance of the algorithm, the so-called ROC curves. The red curve is the best. In this case, you want the curve to be as close to the origin as possible. A perfect curve would be going from the origin, extend to the right and extend up. Right? You're familiar with ROC curves. You know how to interpret these curves. This shows the different performance of different algorithms. And, the algorithms of of our paper published in 2008, 2009 corresponds to this red curve. Of course, as time progresses, more efficient and more effective algorithms are developed. It shows the 3 different algorithms with very different performance results. At a fixed hiding ratio, detection performance decreases as image complexity increases. As the hiding ratio decreases, the performance decreases. As the image complexity increases, the detection performance decreases. This is another bar chart representation of a similar result. The 4 groups shows different hiding ratio. The chart on the lower right shows a very low hiding ratio, which becomes extremely difficult to detect anything in it. And within each chart, as we move from the left to the right, the image complexity increases. You see, again, generally, as the image complexity increases, the detection performance decreases as expected. So the important thing is to how to develop an algorithm that can give you a good performance with high image complexity and low hiding ratio. As I said, an arbitrarily difficult challenge. Again, within each group, there are 6 bars showing the different performance of 3 different algorithms. All right, the same conclusion. Image complexity affects the detection performance, as does the hiding ratio. Our method outperforms other previously published well-known methods, the histogram-based and the Markov algorithm-based. All right, talking about hiding data. Sorry, I lost the sequence here a little. All right, this is again animation showing you how do you hide data in JPEG images. Instead of modifying the AISP of each pixel, about 10 slides ago, this shows you how to modify the DCT coefficients one by one and scan it kind of diagonally in one algorithm to encode the payload. All right, so this is a second class of algorithms for detecting transform-based images. And again, without going into too much detail, general idea is to use a Markov approach to look at the coefficients within a A by A block, and based on that to develop heuristics, the statistics, and use that as features to train your learning machine, and then test it on a set of test data. In one of the papers we published several years ago, we extended the Markov approach to include not only intra-block information, also inter-block between 2 adjacent A by A blocks. It's certainly another thing that can be taken into consideration. In other words, here's the heuristics. The discrete cosine transform neighboring joint density is modified when you embed some contents into your, say, JPEG image. which will result in a corresponding change in the Markov transition probability. Based on that, we can formulate a set of features to train the machine, and then test test the machine that has already learned from the on the training data. There was a paper published in AC and Multimedia in 2009, and another paper about audio in 2011. And pretty much based on the same idea, using the Markov transition probability in combination with inter-block and intra-block information to extract corresponding features for detection. All right, this shows this is the cover, the original image. These are two different steganography algorithms, and you'll see the pictures. You know, the naked eye absolutely cannot see any difference between the CE pictures. But when you blow up the probability distribution, you see, the CE distribution at the bottom certainly are more visibly different than the CE pictures. Right? In terms of the magnitude, this one has much lower magnitude than the one in the middle. Again, you blow it up in the middle. In this region, you'll see the disturbance there once the picture has been embedded with something in it. Well, I will skip all these results, these kind of the self-promoting results, showing your results better than others. And as I said, this really needs to be taken with some objective common criteria. And with respect to the same training set, right, for the comparison to make sense. And that's what we did. All right, usually you do a lot of tests, 50 experiments, tenfold validation, more that standard learning machine methodology to determine the performance of your machine classifier in this case. By the way, we also have another paper talking about how to make multi-class classification. So the ordinary algorithm tells you whether the given image has something in it or not. It's a binary decision. Right? Gives you absolutely no information about what kind of steganography algorithm might have been used to produce the steganogram. Right? Then it becomes a multi-class classification problem. Again, it becomes much harder. We'll briefly talk about audio. Sorry, I couldn't move my audio file here. So this one just shows, again, similar situation, two voices. One is embedded in the other. There's absolutely no way to tell the difference. It's just one simple example, right? In fact, you can use audio stream as the cover for anything. You can carry an image in an audio stream. You can carry a video image in an audio stream if it's large enough, of course. You can carry an executable in an audio stream. The idea of digital steganography is you can carry everything, anything else. Both are digital, right? It's as simple as that. As long as there's enough room for you to hide that something. As long as the cover is big enough to accommodate the payload, right? The idea here, again, going into how to extract features to detect audio steganography. We found out that using Fourier spectrum using these Fourier spectrum is a good way to go about it. Specifically, take the second order derivative of the Fourier transform of the audio signal. Becomes good, gives you a good clue whether the audio has been modified or not. And so here's the basic idea. The derivatives of the cover signal and the steganol signal have a different high frequency spectrum. The idea is one, you take the Fourier transform, 2, take the second order derivatives. In 3, look at the high frequency spectrum, because the low frequency is hardly you can see hardly see any difference, right? So here's a 2009 paper showing how to detect steganography in wave audio. This is wave represents the uncompressed medium, which will be somewhat similar to the uncompressed images. Right? It's easier to detect than the compressed signals like MP3. And for MP3, we have other methods to deal with it. Right? This is let me skip all these really nuts and bolts of how to do the detection. The spectrum of the error derivative, again, if you blow it up in this section, you see in the high frequency range, right? It becomes more evident. It has deviated from the normal, from what you would normally expect. Right? So take the second order derivative and look at the high frequency spectra. You'll see the difference. It's what we call derivative-based audio steganalysis, which we use in ACM transactions on intelligent systems, I think in 2011. One paper there. Here's another audio that I will not show, which just tells you the difficulty of detecting audio steganography. Well, when you hear these two, one is kind of a noisy, the other is rather clean. So if you just make a guess, most people will guess the one who sounds pretty noisy will be the steganograph. It has been adulterated, when in fact it's just not the case. One is the voice of a woman, the other is the voice of a man. There are a lot of other things that need to be looked at, not just what you hear, so to speak. But again, that's not a surprise at all. All right, so in still another paper, we use CEPSTRUM features to detect hidden contents in audio stream. I'll skip this because this is not a part of what we want to propose here. If anybody is interested, the paper is in the 2009 IEEE transactions on information forensics and security, talking about this idea of using CEPSTRUM features to train machines. By the way, we use a variety of machines, SVMs, and neural networks, and other naive-based, everything that we can have a tool for. The ordinary toolbox. We try all this learning machines with the same data. Of course, you want to present your best result. Whatever machine gives you the best result is the one you want to present as your algorithm. And depend on the problem, different machines might come out to be the best contender. All right, this shows the ROC curve for the signal-based versus wavelength and derivative-based detection performance. You can see in each group, you will see curves showing the result of 3 different algorithms. The key is to look at the second order derivative, right? And combine it with the Markov transition features of the signal to as your base features for detection. And these are the these different rows represent different steganography algorithms. And the mean testing accuracy is listed at the right. The signal complexity divided into low, medium, and high. That's the first experiment to kind of group the result into different complexities. All right. That about sums up the basic technique of detecting steganography imaging audios. For videos, it's just a sequence of frames. Each frame will be an image. But audio, in fact, you can also embed the content in header files in other locations. As well as image steganography, you can certainly embed the content in the header files and other so-called metadata areas. But those are relatively easy to detect, so we did not investigate those issues. Those are fairly easy to identify. Right, coming back to the general problem of detecting steganography and how does it relate to software IV&V, because there are a lot of issues, right? Beyond including IV&V, there's pretty significant expansion of the traditional activities. And, you know, who's going to pay for that will become a problem. Because normally, if you want really to do a good analysis, likely you have to use pretty powerful computers and run a long time to detect whether there's something hidden in it or not. So discover better features to improve detection is one issue. That's, of course, that's the machine learning issue. But what features are better in giving you a clue? This is really a peripheral problem to IV&V. How to find better features than a pattern recognition problem. And what we're doing is to analyze the computational complexity, because if you want your company to scan all the incoming multimedia, for example, or scan all the outgoing multimedia for hidden contents, you know, the cost could be rather significant. All right, then I will end here. Usually it destroys pretty easy, right? You can do a number of things to destroy it, but that does not let you to find out what is hidden in there. That's some most interesting thing. What if your colleague sends you a picture of a birthday party? What is hidden content in it? How does the organization know what is in it? And how to find out how to find that out? That's a really serious challenge to not only to software development, also to the general cybersecurity area. Okay.
Thank you very much.
All right. Thank you.
So we'll take any questions for Andrea over in the breakout session.